And Brian is here. Yeah. And Sean.
Yes, Chu is here. I know that. Where's Sean? Do we know? No. Are we just missing Sean?
Yeah.
Are you sure?
Yeah.
I think so. We are not that sure.
Alright, if you can write this down. Jerry, you're taking all the heat. There's none left for everyone over here.
No.
Come on, be a man. Come on, sit down over here. No, come on. Come on, it's good for your health. A little bit of cold air, toughen you up.
Here?
Yes.
Here is dinner.
It's much better if you just get used to the cold. It's better for you.
I think this place is cooler than that.
What? What is that?
Be strong, Jerry. Be strong. Be strong. Alright, did you write that down? Yeah. So we're looking at a model of a gas here. Continue? Yeah. Okay. Right. So, we know what pressure is. It means how much something is pushing on something else. And I think we've done the formula already. Yeah, no, we have done it already. Do you remember the formula for pressure?
F over A.
Yeah, F over A. And what's the unit we use for pressure? We actually have two units we can use. Pascals, yeah. And the units are pascals. And we say that 1 pascal is what?
1 Newton per meter.
Oh, so close.
1 Newton for
Per meter squared.
no.
Yeah. 1 Newton of force at right angles to 1 meter squared. Okay. It's the same as that. I would like you to write this down again because it's a common enough definition on the exam asking what a pascal is. So if you can just write the formula and the definition down again. Monica, could you move the projector a bit to the left, please? Yeah. Cool. Okay, got that? Yeah. Bruce? Okay. Let's continue. Got that, Bruce? Bruce? Bruce, hello? You got that? Oh, come on, Bruce. How long is this taking? You got it?
Different.
Yes.
She said right angle over on area of 1 meter squared.
Correct.
Yes.
I mistyped it. Stuff happens.
Native difficult speaker makes
Yeah.
and English.
I never. Hang on. I never said I was perfect. I don't know why. I'm flat that you think I'm perfect, but I never said I'm perfect.
I'm saying he thinks he's perfect.
Well, he is.
What?
I thought everybody knew that. No. All right, let's continue then. Okay. You got this now, Bruce, I hope?
Yeah.
Yes, okay. Right. Now, let's think about exactly what we mean by an ideal gas. This might be a word you've heard in chemistry. I don't know if you have. Have you done this? Ideal gas in chemistry with Lorraine?
No.
Yeah, she talked about
Yeah.
it.
Yeah?
Oh, yesterday. Convenient.
Ideal gas.
No.
She literally mentioned this yesterday.
Yeah,
PV equal.
Find ideal gas.
Okay.
Dude, that was yesterday. Right, so, did she talk about what assumptions you need for an ideal gas? No. So an ideal gas is a special type of gas. We shall assume a couple of things about an ideal gas. Number one, oh, and I should say, I've seen it in the exam once or twice where they ask, what are the assumptions for an ideal gas? So these are the assumptions for an ideal gas. So the first assumption for an ideal gas is that it has low density. That's the first assumption. So when we talk about an ideal gas, we often talk about a gas which is low density. But if you think about it, most gases are low density anyway, so that's not a huge assumption to make. Okay, that's the first assumption. Second assumption, it's colliding particles. So we picture the gas as molecules just bouncing off of each other, like lots of ping pong balls, something like that. Got that? And the third assumption for an ideal gas is there's no attraction between the molecules. So it's not like, for example, it's not like the molecules are charged. If, for one example, a molecule was positive and another molecule was negative, what would happen? They would move towards each other, yeah. So we say there's no attraction between them. And 4, we ignore gravity. So we don't consider gravity acting on the particles. Now, of course, in real life, gravity does act on the particles, but because the particles are so small, the force is so small, it's not worth considering. The potential energy from gravity for a molecule is tiny. It's not worth considering. The kinetic energy will be much, much, much bigger, so it's only worth considering the kinetic energy. Yeah. So please note these 4 assumptions, because I have seen questions in the exam, like for 4 marks. What are the 4 assumptions? Yeah, 1 mark each assumption. Yeah. Now, they should be easy to remember, because if you think about it, they all kind of make sense. The gas is a low density, its particles colliding into each other. There's no attraction between the particles, and we ignore gravity. So that is balls. Small balls bouncing around in a box. That's our picture we have for the gas. And that's important, because we're going to prove something now which is quite difficult. No gravity as well. So this is basically the picture we have in our mind of the ideal gas. And let's look at what formula we can make. Now, before I begin the following proof, it's important to say this proof is too long for it to be all in the exam. However, they may ask you to prove parts of it in the exam. So what I have seen in the past is, Sean, come on, what happened to you?
A long history. Sorry.
But
It's a long story, is it? Is it really? Can I summarize the story? That's what I thought, yeah, go on. And then?
And I eat breakfast.
I thought it is too early, so I want to sleep for a while.
Yes.
And open my eyes again at 8 o'clock.
Okay. That's not really a long story. That'd be a short story. Okay, so what I was saying is, what I've seen in the exam is they don't ask you for the full proof, because the full proof is quite long. But what they have done is they might ask you for the first part of the proof, or they might ask you to explain a middle part of the proof. So it is good to see the whole proof and to understand it, because they will ask you questions on it. So let's have a look at the proof of a formula which you haven't seen yet. Okay, right, so like I said, we'll start off by thinking about our gas in a box. Okay, so we have a box, and we'll make it easy. What we usually do is we'll just say the box is L, L and L. And we'll also make it easy. We'll look at one particle, and the particle, we'll have it start in the center or something. Moves across, bounces against the wall, moves back, bounces against the wall, and so on. So it's just going left and right, bouncing like that. And we want to look at what's happening here when it hits the wall. This is where it'll be interesting. Okay, so let's draw this here. Let's have a look at the wall on the side here, and here's the particle, and it'll come in and hit the wall. So it's coming in with a speed of, we'll say, u, just to make it easy. So it'll come back out with a speed of u as well. Yeah. So the change in the momentum will be mv minus mu, which is m minus u minus mu, which is minus 2mu, like this. Is that okay so far? Yeah, that's the delta P. Now, I'll divide both sides by delta T, and what have I made here? This is the force. Yeah. Now, this is the force the wall exerts on the particle. You know, it pushes it to the left. That's why it's a minus. What I really care about is the force the wall feels from the particle. So that's the reaction force. So that reaction force is really what I care about. But the only difference with that is no minus. It's just pointing the other way. So I don't care about the minus. So I'll just drop the minus. So I'll call this one, this is the wall, and this one here, the F, that's the reaction, which is what I care about. So that's 2mu over delta T. Okay, and just a little bit more here. We have the formula, pressure is force over area. So that means force is pressure by area. So now I get this formula, pressure by area equals 2mu over delta T. Now I'll just stop for a minute to let you write this much down before continuing. But this is what I have so far.
See, but don't we lose its speed when it bounds?
Say again?
When it bounds.
Yeah.
Doesn't it lose
It does. It does in real life. For our simple model, we won't consider that. Yeah.
Could we close the window?
Okay.
Yeah.
Yeah. But I think that window's broken, isn't it? Bruce, can that window close? Try. Nope. Good man. Better?
Later.
Later we'll see, okay. Okay. Yeah? Continue?
No.
No? Okay. Yeah. Okay. Continuing. Yeah. Okay, that's true. No, that's true, Bruce. So far, is this okay? We can follow everything so far, I hope. Yeah.
A rho equal S.
Sorry, that's not a rho. I was thinking it looks like it's a P for pressure. I know. Okay, so if I just write up here, how far does this particle travel in one cycle? Right, bounce, left. What's the total distance? 2L. So we know we have our distance, speed, time. And time is distance over speed, isn't it? Yeah. So what's the distance? 2L. And the speed we said is U. Okay, so we're going to take this and put it in here. 2L over U. So I get PA equals 2MU 2L over U. Now that's nice because what cancels here? The 2's. So now I have PA equals MU squared, over L. Now I'm going to bring the L up to the left. Just divide it by, But what's A multiplied by L in this picture? Yeah, if you remember, A is L squared. So A multiplied by L is L cubed, which is volume. Yeah? So if I continue back down here, I get PV equals MU squared. Now you might start to think, this is looking a bit familiar. If you think about your chemistry yesterday, if you can remember that. Yeah? Okay, can I continue? Yeah?
Oh, I have to write that down.
It would be a good idea. Yeah? One problem though is that the particle is not moving left and right. Realistically it's moving all around the box. So we need to fix that now. But it's actually not too difficult to fix. If I can go to the side, we'll fix it. Can I scroll left? Yeah? So, here's the problem. We said we're thinking about the particle moving left and then right. But of course, realistically, the particle is moving in all different directions as it hits. Let's say its speed it's moving in each direction is v. So I'll just try and draw it in 3 dimensions here. So we'll just imagine it's going off here at v. Now you realize, what do we normally do when we have problems like this? Well, normally what we do is we resolve. We find the components. The only difference is we have 3 components. 1, 2, and 3.
Yep.
I don't know what these components are. I'll call them ux, uy, and uz. But what I do know is that ux squared plus uy squared plus uz squared should equal v squared here. Not 0. And you realize for each particle, its speed will be different for each direction. So some particles might be going left, some particles might be going right, some might be going up, some might be going down. But we can say reasonably, on average, the ux squared should be about the same as the uy squared should be about the same as the uz squared. Think about what would happen if this wasn't true. Imagine for most particles that uz squared was bigger than uy squared. If that was true, what would be happening to the particles? They'd all be moving upwards. If on average the z direction was bigger than the x or the y direction. So we can say that these are all about the same thing. We'll call that u. So u squared plus u squared plus u squared is 3u squared. So that means u squared is 1 over 3 v squared. So actually, to go from 3 dimensions to 1 dimension, all I have to do is divide by 3. And that's all. So the u in the x direction is just 1/3 of the v squared in the 3 dimensions. So this gives us a very easy way to fix this. All we have to do to make it 3 dimensions is actually just put in a 1 over 3. And now it is in 3 dimensions. So a very simple way to fix it from 1 to 3 dimensions. Let's see. If I have this picture here before I had this was originally 1 dimension. Yeah. So what about if the v is in 3 dimensions? Well, I need to look at what's happening in 1 dimension. In 1 dimension, it'll be 1/3 v squared. So in other words, I can just put in a 1/3, and I suppose I should really then change that to a v then. Yeah, right. I shouldn't keep it as the u, because the u was for this. U squared equals that. In other words, I can say u squared equals 1/3 v squared. That's what I'm saying here, and I'm just subbing that in. So I have pv equals 1/3 mv squared. Now, when you look at this, mv squared should remind you of something in physics. What is it kind of like? What formula has mv squared in it?
Half mv squared.
Yeah, what is a half mv squared, Jerry?
Potential energy.
Ah, Jerry, it's the other one. Kinetic energy, yes. So what I'll do is I'll put a 2 here and a half here. And now what does this become? Kinetic energy. But what is potential energy here? That's, we said, roughly 0. Why do I say it's roughly 0? Too small, yeah. It was one of the assumptions. We said we ignore gravity. So if I put this result in, I get PV equals 2/3 KE plus PE. It's basically nearly 0. But what is kinetic energy plus potential energy? Total energy. So I get PV equals 2/3 the total energy. Or in other words, I get energy is 3/2 pressure multiply volume. Important result.
Wow.
Amazing. No, it will ask you to do a part of it. So for example, the last time I saw this on the exam, I think it asked you to calculate a formula for the force. And then, I can't think of what else they've done. I think they might have asked, and then the time before that, they asked for the 4 assumptions for the ideal gas. It's too long of a proof to have the whole proof in the exam, but they will test your understanding of it. Now, you're probably not realizing how amazing this result is, so let me explain why it's so amazing. Yeah, and let me give you some insights. So the reason this result is so amazing is, if you think about it, this E is the, it's basically the energy at a microscopic level. It's the kinetic energy plus the potential energy. Actually, I suppose this is the energy for one particle, but if you have like 1 million particles, all you have to do is multiply this by n. So you have like the total energy then. So I suppose if I want to be a little bit more accurate, if you want, this is the energy for one particle. So the energy for all the particles would just be, you keep adding them all up. You know? But if they're all the same, then that's just n multiplied by E. If you multiply n by E, all you're doing is you're taking this here and multiplying it by n. So if you have one particle and you multiply it by how many particles you have, then this m just becomes the total mass. So then it just becomes the total energy. So anyways, my point is still the same. This is for the total energy. Total energy. Yeah, I have to put in an n in here. Let me see. Yeah, I'll put in my n here. That's for total. We multiply it by how many particles we have. Do we know how many particles we have? Well, we could, because you have a formula in chemistry. The PV equals nRT. But we haven't done that in physics yet. So we don't know in physics yet. So what we'll do in physics is we'll cheat a little bit. We'll take the total energy and we divide it by n. So think about maths. If you have a total and you divide it by how many you have, what does that represent? Yeah, what's the word? Yes? Yeah, but there's a word for this. Average. So, does anybody know what symbol you use to represent average in maths? No. No. You put a little line on the top like this.
Oh, yes.
Yes. So we have this result. The average energy is 3/2 PV. This is the total energy. Yeah, is that okay? Yeah. Let me just have a look here. I hope I wrote that down. I mean, put in the slide. I'm sure I did. Yeah. Actually, hang on. I think I made a mistake here with my n. Let me just think about this. I don't want to give you something that's wrong. Sorry, let me just think here. I finished up here by saying pressure by volume equals 2/3 the energy for one of them. That means 3/2 pressure times volume is the energy for one. If I want the total energy, I should take n and multiply it by E. Yeah, no, that's it, isn't it? And then that's n multiplied by 3/2 PV. That's the total energy. Yeah, and then if I divide by n, I get the energy for one of them. Yeah, okay. So this is the formula that we have. I should really have a little bar on the top of the E here then. Maybe when you write it down, make sure you have the bar on the top. You got that?
Huh?
Yeah. And my spider senses are telling me I did something silly with the N. It's good to listen to your spider senses. This is I'm happy with that. Yeah, the total divided by how many you have. Yeah. Yeah, because they're all about the same anyways, so... Anyways, maybe I'm thinking about it too much. So, why is this important? This is important because this is microscopic. It's impossible to measure the energy of a molecule. It's microscopic. You can't just, take out a ruler and measure it. But this here is macroscopic. It's easy to measure pressure and volume of a gas because you just, there's machines to measure pressure and you can just measure the volume. So the reason this formula is amazing is because it's letting you switch between the two. The average energy per molecule, you can know that by looking at the pressure and the volume. That's what makes this result, surprising, that you can link the two like that. That's the insight here, yes. You got this? Isn't it just? Okay. Did you write all of this down? Yeah, you have all this? We can continue? Okay, so I think I would have said what makes it interesting. Right. Okay, so we have another formula to look at which is easier to prove. So this is how much energy, we can use this to find out how much energy we have in the gas. But suppose I want to do something like I have a gas and I want to change the pressure or the volume. So maybe, for example, I have something like this. And there's a gas in here. And then what I do is I have a force and I push it to make it smaller. So the volume and the pressure, it changes. Yeah. Obviously I'm doing work. I have to do work to push it, to close it. So how much work am I doing? Well, let's calculate it here. So let's imagine I push it this much. I'll call this distance here, I don't know, D. Yeah. So what's the formula for work? You remember this. Force over distance. Sorry, force multiply distance. Well, I wrote the right thing, I just said the wrong thing. Force multiplied by distance. But you also know that pressure is force over area. So we could also say force is pressure by area. Yeah. So this would be pressure, area, distance. But what exactly is area by distance here? If you, yeah, but now just be careful. Not quite, it's nearly V, but it's not quite the V of the whole gas. It's the V of this part, the part that you reduced it by. So we shouldn't call it V. Instead, maybe we'll call it delta V. How much volume you lost. So we get this formula, pressure times the delta volume here. That's the work. But you can do the same thing. You can, you could have done it the other way. You could have kept the volume the same and changed the pressure. You could have done it like this. You could have kept this the same, but then increased the pressure. You could have done it. You could have changed the P here. So in other words, the work, we can just say it's the change in the pressure times the volume.
What do you mean delta P multiplied with V?
Just the change in PV.
That's But P never change.
Yeah, so usually, yeah, you're right, Jerry. So usually in the question, it's just like this.
P doesn't change.
Usually in the question, they don't change the pressure. They keep it the same. But of course, you understand that if you're shrinking the gas down, the pressure is increasing. Sometimes in the question they say, oh, the pressure roughly stays the same. I mean, if the pressure does change from, say, P1 to P2, and you want to keep it constant, you could say that the pressure is roughly P1 plus P2 over 2. You know, that's one way you could deal with it. Usually what happens for an ideal gas is the pressure is quite low to begin with because it's a low density. So when you shrink it a little bit, the pressure doesn't change much. The volume changes much more than the pressure would change. Okay, continue. Yeah. So the work done is the change in the pressure and the volume. To change the gas's pressure and the volume. That's how much the work's done. Okay. Next, we'll look at the pressure on a sphere submerged in a liquid. And we'll look at the formula here. So we have another formula to prove. I know. Okay, so let's say here is our liquid. And here's our sphere. And we'll call this distance here, we'll say that's D. Yeah? Or do I want to use a sphere? Or maybe it'd be easier if I use a cylinder. I'm trying to think what's easiest. Alright.
When is the start point of the
The start point is at the water level here.
surface?
The surface, yeah. Okay. So if you look here, there's pressure on this. You know what? I'm going to draw this a little bit neater. I don't want to make it a sphere. I want to make it a circle, like a coin. Like imagine this is like a €1 coin. I'll make it a little bit easier. Or 2. It's fine. Okay. So let's calculate the pressure here. Pressure is force over area. Okay, well what's the area? If this is a little coin with radius r, what's the area? Pi r squared. Now what is the force though on it?
mg.
Very good, mg, but m of what?
No. mg and
No, it's the weight of the water that's above it. All this water is pushing down on it.
okay.
Yeah?
But also have mg.
Oh, you were thinking mg of the coin?
Because I win a coin just on the water, and there's no water on screen.
Oh no, we're just looking at the coin in the water.
Okay.
Yeah. So mg. Now, do we know the m? We don't, but we have this formula. Density is mass over volume. So mass is density by volume. So this is density volume g over pi r squared. Now what's volume? That would be pi r squared d, h in this, the d in this case, g over pi r squared. Now what cancels here?
No dt.
Pi r.
Yeah, that's gone. If you want, you can call this h. I don't mind, h or d, whatever. So you get pressure equals rho g h or d or whatever, yeah. So what happens if you make the h bigger?
Pressure is bigger.
Pressure is bigger, which makes sense. And what's also interesting is it important how big this is? No, because what happened to the or? It cancelled. So in fact, this could be just a little point. So if we make the or go to 0, we have the pressure at a point is rho GH. Yeah. But you kind of knew this already. The deeper you go into the water, the more pressure there is.
Yep.
Yeah? Okay, continue.
Yeah.
Now, a little bit of a definition. If you think about it, this also works for gas. It doesn't have to be a liquid. And right now, I'm in a liquid. I'm in an ocean of air. Yes? So there's pressure on me. There's pressure on me from all the air that's above me, pushing down. How much is that pressure? We call that 1 atmosphere of pressure. And it's a pretty big number. Does anyone know it? Yeah?
101.
101 what?
350.
What unit? Pascals, yeah. Or 101 kilopascals. Now that's a lot. That's a really big number because that's 101,000 newtons per meter squared. So there's a lot of pressure from the air above me. I just don't feel it because we're born into it. So, yeah. It's pretty big. This is the pressure at sea level. Of course, if you climb up a mountain, what happens to the pressure? Lower. And if you go into a valley, it's increased, higher pressure. This is from the air pushing on you. It's pretty big. Can you make note of this value? 1 atmosphere of pressure is 101.35. That should be a small k, kilopascals. What the heck? Come back. There you go. Okay. You got that?
Almost. Okay.
You got that? Okay, so let's continue then. I think we have some examples to look at now. Right, so here's a simple one. What's the pressure on you if you're swimming 5 meters below the sea? Well, I use this formula that I just have. So pressure equals rho GH. Okay, what's the density of water?
1,000.
Yeah, actually I suppose if we're being precise, I did say swimming under the sea, which is salt water, isn't it? 1030. The G is 9.81 and the H is 5. Okay, we won't bother, we know how to calculate that. Pascals. Yeah. Okay, let's have a look at the next one. How thick is the Earth's atmosphere? 1 meter? You got a problem then if you're more than 1 meter tall.
How do we calculate that?
How thick is the Earth's atmosphere? Yeah. So here's the Earth and here's the air above it. And my question is basically, how thick is this? In other words, when will you have a problem? At what height? So let's calculate it. We can actually calculate this. If you think about it, we're on the bottom here. We have the formula pressure equals rho GH. But we know the pressure here. What is it? It's 1 atmosphere, which is 101.35 kilo. Pascals, yeah. Now, the density of air we don't know, or yes, it's about a kilogram per meter cubed, roughly, the density of air. So we'll say that's about 1. And the G, it's about 9.81. So it's about 9.81. And the H is what we're looking for, how deep we are in the air. Now, if I just say, to do this in my head, I'll roughly say this is 10H. just to make it easy. So I get h is roughly 101.35 times 10 squared, which is 10135 meters, which is roughly 10.1, about 10 kilometers, roughly. Now this is only an approximation. It's not the exact answer, but it's not bad. In fact, the true answer, I think, is 20 kilometers about. Why is it not exact? Well, the reason it's not exact is because the density actually changes. So here, maybe it's about 1.2, but up here it could be about 0.2, you know, so it changes. And in fact, also the G changes as well. The G is maybe here it's 9.81, but when we go up a little bit higher, maybe it's like 9.5. So usually, because of this, it means our answer was only an estimate. This would be like sort of a middle value. So the true answer would be twice this value. So I would estimate it at about, you know, 10. Calculate this. We needed to know the pressure. But we know how to work out the pressure. We can have something called a barometer. You see them in classrooms. They're up on the wall. They tell you what the pressure is in the room. So that was easy to find. What else did we need to know? Density of air. We could do an experiment to work out the density of air in a lab. You know, it's not too difficult to do. Just put some air into a container, measure its mass.
Why are my hands freezing the most?
You're from Kenya. You're not from Malaysia. Malaysia is even hotter. I mean, you're from somewhere cooler, so you should adapt to this weather.
I don't see your weakness. I
Yeah.
don't see your
Oh.
Yeah, thanks. Go put your hands in your pocket and you can mix. I know you're just going to the toilet, but if I did now, I'll keep them clean for you. Password.
This is what I feel like.
What is Drew singing for?
I feel like.
Sharing is caring.
You are so up. So up. Oh wait. Why you
It's so warm here.
Oh. Warm face.
Okay, see like I'm being cool over here.
You're really cool.
Barbecue.
What are they from?
So here's cooking.
最近家去吃火锅，还是滑雪。
Go away.
Today I want to cut my hair. Like we have 2 hours to wait. 2 hours to wait. Wow. Last time it. The day before yesterday.
You have short hair though.
Yeah, you should look good this.
Yeah, but I'm full. Come on.
No, you should use hot water. I think the heat here is hotter than that one.
I should stay at home. Why you have losses? I used to you do the deep.
What's the problem?
You stick to his friend, you ask him what's your problem. What the heck?
They tell me
What the heck is wrong with you? What is it?
You were so warm.
What do you want?
Shit.
I'm also alive.
What?
Alive.
What's
Alive.
that?
Alive.
Alive.
Don't you need
I will say again.
to answer like
我在看英雄，这是王者。
哦，
王吗？
啊，我房屋7500。
我干嘛？然后有什么那个吗？配方之类的？
配方。
我也不知道我在说什么，就是策略吗？
Come on, why would you do all of this? Come on, don't do that. I want. What? 我想一偷听。
哦，哎，后呀，后呀，我那你们。
Yeah, you do.
Guys, just really briefly, you can watch this in the video later, but I made a small mistake in my proof at the end. I was right to sense my spider senses as a mistake then. So just the correction I want to make at the end is that when I said PV equals, what was it, 2/3 energy for 1, if I look at all the particles, then this is just n multiplied by all the particles for the total. But n multiplied by the energy for 1 is the energy for all of them. So my formula is actually 3/2 PV and not what I had. Average energy is 3/2 PV. So that's a small correction. This is wrong. It was actually the total energy, not the average energy. This is at the end of the video, so when the other students come back, I'll tell them to watch the last 1 minute of the video, and I'll stop the video now.
Bye.
Now, once I stop the video, we can talk about all the students we don't like who aren't in the room right now.
Okay.